Okay, so today we have the pleasure of having Zoe Wyatt, who's from Melbourne, but now based in Cambridge. We talk about stability problems in general relativity.
Okay, thank you very much. Thank you all for being here. I really appreciate it. And I should start by saying thank you to the SMRI, the Mathematical Research Institute, because they're hosting my visit at the moment. I'm going to tell you about stability problems in general relativity. And my understanding was that perhaps not everyone here has studied general relativity. Good. So I'm just going to keep this very high level, give a bit of an introduction, tell you about some of the maths that we ask. Okay, so I'm a PDE analyst. Concretely, I study PDEs. I'm going to try and explain to you where these PDEs come from. And then hopefully at the end, I can just tell you a bit about, some of the research that I've done recently, in particular, a paper that came out on Archive joint with two co-authors in this direction. Okay, so let's talk about general relativity. And maybe I'll just start by reminding you of Newton's theory of gravity. Okay, and you can say lots of things about this. Let's just say 2 points. Let me just say 2 points. First, gravity's a force here. Okay, and it's acting between masses. So you think here I've got the mass of the Earth and the mass of the Moon, and I have a force that acts between these two. And obviously the masses are different, so that's why there's a relative difference. And this is just this kind of motion is happening in some ambient fixed space. Okay, your time and your space. It's just happening in this ambient kind of fixed world. And this is, how we can understand gravity, okay, to a high degree of accuracy. So Newton's gravity is correct, but there are certain things that we need to do to correct it. And maybe I'll briefly mention a couple of the where you might need this more nuanced theory of gravity. Okay, but the theory is, so it's Einstein's theory of gravity, which is called general relativity. And mathematically, it's the study of manifolds. Okay, so this is a manifold M, which has 1 time and 3 space dimensions. Okay, so this is why I call it a space-time, because this manifold is unifying space and time. Okay, points are labeling points in space and time. Okay, the manifold is equipped with a metric G. Okay, and that metric G it's crucially not Riemannian. Okay, it's pseudo-Riemannian. In particular, it's Lorentzian. Okay, which is a way to say that its signature is of this split signature here. So minus plus plus plus, or let's say if you do quantum field theory, you might do plus minus minus minus. Okay, but there's a difference there. Let's say 0, 1, 3, 3. Okay, so this is the objects, let's say the mathematical objects in general relativity are these manifolds. And it's good to keep in your mind that these are dynamical manifolds. Okay, these are things that are changing. Now, we call this manifold a spacetime, okay, if it satisfies the so-called Einstein equations. So the Einstein equations, on the left-hand side, it's something involving curvature. Okay, it's the Ricci tensor. This is a contraction of the Riemann curvature tensor. Okay, so on the left-hand side, we have some notion of curvature. And on the right-hand side, we have another thing which I've just put here as matter fields. Okay, we have matter on the right-hand side. So this could be 0. You might not have any matter. You could be in vacuum. This could be electromagnetism. Okay, this could be a Vlasov field. Lots of different things you could put on there. Okay, this could be a relativistic fluid. Actually, that's something I study. It's a relativistic fluid on the right-hand side. Okay, so these are the fundamental equations of general relativity. Unfortunately, I can't really, tell you why these things. Why am I considering these manifolds? Why do I get these equations? Okay, that's in a course in general relativity. But let's maybe just unpick a few things that this tells us. Okay, so first thing just to bear in mind is that space and time are connected. Okay, in some sense, we're not quite seeing this here, I appreciate, but just think of the fact that the points in the manifold label points in space and time. We're kind of setting up the problems so that they can be connected. This is very different to Newtonian gravity where time and space are fixed. Okay, and we often say this is our most accurate theory of gravitational force dating from 1915. Now, if you look at this slide, you're probably like, well, where on earth is gravity? Like, I've used the letter G for the metric. And you're like, G for gravity, that seems promising. It's true, okay? It's not clear. Where is the gravity? And so this is, I guess, what just the little idea I want to convey. Okay, so let's remember that if I want to take the shortest distance between 2 points on planet Earth, it will not be this red line here, which is a straight line in flat R2. okay, it will be a curved line because the Earth is curved. Okay? The Earth is a sphere. So geodesics on the sphere, they're not kind of flat lines, or the flat lines in some sense are these curved great circles, this purple line here. Okay. So in a similar way, gravity is going to cause this curving. Okay, and particles are going to travel along geodesics of a curved space-time. Okay, not just a space, but the unified manifold, the space-time manifold. Okay, so the gravitational force is, let's say, manifested through this curvature. Okay, so you often see this quote by Wheeler. Okay, and the first part, physicist Wheeler, first part says space-time tells matter how to move. So what this means is that I have my space-time, I have my metric G. That metric is curved. Okay, that curvature produces curved geodesics. And my particle, like my moon here, travels along geodesics of that curved space. Okay, so the gravitational force is somehow causing, you can think of it as like it's causing this curvature. And then this particle here, whereas before it had the force, okay, the force of gravity was acting here. Now it's just traveling on a geodesic, okay, path of least action. Now it's just traveling on a geodesic, but it just so happens that that geodesic is curved in the space-time. Okay, so this is what it means to say space-time tells matter how to move. So we think here of this little mass that says a point particle. And the inside here, we've got the Earth. It's a big mass that's curving space-time. That's causing this geodesic to be, bent from Minkowski, bent from flat Euclidean space. And it's telling this particle how to move. But if you remember the Einstein equations, on the left-hand side, I had the Ricci tensor. On the right-hand side, I had matter fields. Okay, so it's a nonlinear system. And this is the second part of this sentence. It says matter tells the space-time how to curve. Okay, so the matter of the Earth causes curvature around the Earth. Okay, the matter of the moon causes curvature around the moon. Okay, so we have energy can also cause space-time to curve. It doesn't just have to be matter like we usually imagine it. Okay, so this is, let's say, a few ideas in general relativity. Maybe you might like to know where it gets applied. Okay, I said it was the most accurate theory of the gravitational force. And one of the motivations that Einstein had when he was looking to kind of write these equations down was they were doing observations of Mercury, and Mercury's orbit has a shift. It's called perihelion. And the predictions that come from Newtonian gravity of this shift were off by a small factor. Okay, and so he was trying to, let's say, understand where that shift would be coming from, and this is what general relativity solves. Okay. Something else that we get from general relativity. Okay, so Newtonian gravity, the force only acts on masses. Okay, now in general relativity, curvature can also come from massless particles. Okay, so here, we maybe not think about the moon, but think of some beam of light, okay, that's been emitted by some galaxy. Okay, that light can come through here. It will be affected by this space-time curvature. Okay, so it might come in here and it might get deflected and it might go off that way. Okay, so light bending was something that was predicted by general relativity, and it was observed a lot later, I think actually in the 70s. Okay, but then I always like to give this really concrete application of general relativity to make myself feel like I study something that is used in the real world. And that's in GPS. Okay, so global position satellites. So maybe before I put the picture up, you've got Earth, okay, and you've got the satellite up here. The satellite is moving very, very fast. Okay, tens of thousands of kilometers per second. I think it's about 14,000. Okay, so because it's moving very, very quickly, it undergoes special relativistic effects. Okay, now, because the satellite is very far from the Earth, it is further away from the stronger gravitational force or field that we have here on planet Earth. So it experiences a different notion of gravity, let's say. So it also undergoes general relativistic effects. Okay, now these two effects actually oppose each other. So you've probably heard, hopefully you might have heard the phrase before, moving clocks run slow. Okay. So this is special relativity. Okay, these satellites are moving really, really fast. Their notion of time is running slower relative to our notion of time on planet Earth. Sorry, I should say, you might be like, why do I care about the time? The way GPS works is these satellites send light signals, and we know that the signals move at the speed of light. So we have C, and we need one or the other, D or T. Okay, so if we know T, then we can work out D, and distance is good because that's what we're trying to do with GPS. So, so we need to know T really accurately. Okay, the time that a light source is emitted compared to the time that the light source is received. Okay, so knowing time is really important, thankfully, because everything moves at the speed of light, and that is a fundamental. Okay, so special relativity. So these satellites move very, very quickly, and that means their notion of time runs slow. So I think this is what is put kind of on this picture here. But they're also further away. I think it says here at about 1,000 kilometers. Not entirely sure about that, but anyway, it was 20,000, but there you go. I don't know numbers. So the satellite is further away from Earth. Okay, gravity is the curvature in space-time is coming from planet Earth. Okay, so we have a weaker gravitational field up here. And if you just kind of think of the idea that gravity is kind of pulling things down, okay, it's also then essentially slowing down time in that process. Okay, and so this means that in fact, when we're further away from the source of gravity, when we're up in space, time runs faster relative to the clock on Earth. Okay, so these two different effects give you some cumulative effect, and the numbers like 40 nanoseconds or something per day. It's very, very small, but it's the kind of effect, if you didn't include it, our GPS would be off by like 10 kilometers per day. Okay, so it's something that is kind of very much needed for GPS to be accurate. Okay, so there's an application of general relativity. And now let me tell you some of the math. So remember, we're looking for a Lorentzian manifold. Okay, so manifold M with a metric G that satisfies the particular equations that I'm interested in. Ricci, and then whatever matter field I have on the right-hand side. So I just want to really emphasize that we don't know the metric. That's the unknown here. Okay. So the unknowns, let's say another way to think about it, are the components of the metric with respect to some coordinate system. Okay, so here I've used something called Einstein summation notation or summation notation. Okay, so I have a lower index and upper index, and that secretly means that I have a sum going here from 0 to n. 0 is the time index, and n is the top space index. Okay. But you see here already, it's going to depend on the coordinates that I use. Yeah, the value of these components will depend on, if I'm using t or x or t r theta, all those different kinds of things. And that actually, this is kind of going to play a role in the PDE side. So let me give you some examples, okay, of spacetimes, of solutions to this system of equations, to the Einstein equations. So, easiest solution is the Minkowski spacetime. Okay, and the manifold here, M, it's just 1r for time and 3r's for space. Okay, my metric here in rectangular coordinates, the components are -1, +1, +1, +1. If I did it in spherical coordinates, it'd be something different. Okay, but this is my metric. These are different components in this particular coordinate system. Simplest solution we have, Minkowski, the regime of special relativity. Okay, so the next most simplest solution is the Schwarzschild solution. Never know if I say that right. Which I'm not very good with years. Maybe he found it in 1917. Maybe it's not 1919. I think he was in the war. He was in the First World War, and then at the same time, he was like writing down solutions to the Einstein equations, as one does. Okay, so this space-time describes the gravitational field around a spherically symmetric object of mass little m. Okay, what is the number one spherically symmetric object of mass m that we like to think about? It's Earth. Okay, so this is the metric that we use to compute those corrections for GPS satellites. Literally this metric. Now, this metric also has the funny property that if you concentrate this mass into a sufficiently small enough region, okay, you get something called a black hole. There's kind of two very different types of solutions here. One, when the radius for Earth, let's say, is about 2 kilometers. So all the mass of the Earth would have to be concentrated into a very, very small radius, about 2 kilometers, to get a black hole. Okay, or we also just have the Earth, okay, where it's not that compact. Okay, so this is the Schwarzschild metric. So you notice here that there's a lot of symmetry, right? Here there's spherical symmetry. Okay, and here I've got every kind of symmetry, probably. Maximum symmetry. Okay. So what is my goal, right? So my goal is to study the dynamics of space-time solutions. Okay, so I've just given you two special solutions, one the Minkowski, one the Schwarzschild. Okay, and now I'd like to know the dynamics. Are they stable solutions? Okay, and if I perturb them in some sense, they're stable, or are they unstable ones? The small nudges of these solutions lead to something quite different. Okay, that's the heuristic to have. We can make this concrete in the world of modern PDE theory. Okay, I'd like to study the dynamical evolution of geometric data, okay, under the Einstein equations. Right, so you think of, I don't really have a board, do I? Okay, so I have to use my hands. Okay, so you have your space-time. Okay, I'm just going to take a time slice of it. Okay, t equals 0. Set everything off. Okay, that will induce some geometric data, which is going to be in the form of a Riemannian metric, gamma, and a 2 tensor kappa, which we identify with the second fundamental form. Okay, so easiest way to think about this is that I'm going to set time equals 0, and I'm going to specify position and velocity of my metric, very loosely speaking. Okay, and using the position and velocity, I would like to evolve forward in time to uncover the dynamics of that space-time. All right, very much, kind of what we do in mechanics, let's say. Okay. And if I have a known space-time, okay, if I have the Minkowski metric here, well, I know exactly what the position and the velocity are. Well, here they'll be trivial. And I know that if I evolve them forward, well, I have a solution. So I start with Minkowski and I just stay with Minkowski. Okay, and so now the question is, what if I were to add a bump? Okay, a small bump. So unfortunately, my colors changed. I'm sorry about that. Okay, but think here of my original space-time with gamma kappa. This is my original initial data. Now I'd like to add some bump. This is this little bump here at Epsilon. Okay, which I can make rigorous in Sobolev spaces. Okay, but some bump. Right, and the intuition to have, broadly speaking, I guess I want this bump to be small. I don't want to kind of throw in a galaxy's worth of energy, right? Obviously, I'm going to form a black hole. Okay, so I want it to be small. And maybe the intuition to have is that three things could happen. Okay, so gravity is attractive, right? It's focusing. So it is very possible that somehow this extra bit of energy focuses things together in such a way that I get a shock. I get some kind of breakdown of regularity, I get some norms blowing up, something goes wrong. Okay, or it could be the case that actually my little bump of extra energy, it just dissipates away, just disperses, and I end up with the thing that I started with. Okay, that's supposed to be the G0 here. So here I like to think of this one as asymptotic stability. What can also happen is a kind of orbital stability. Okay, and this is what this middle picture is supposed to be. The idea to have in mind is if I have a black hole, typically they're rotating. Okay, if I throw in a little bit of energy and mass, it's going to absorb that. Some of it's going to radiate away, but it's also going to absorb some of that energy. Okay, so the final state black hole that I get, maybe it's rotating a bit faster, maybe its mass is a little bit smaller. Okay, it's like an orbital stability. I know what an asymptote's to, but it's not exactly what I started. It's kind of what makes these stability questions really hard. Okay, so this is, let's say, your hope, your goal, dynamical evolution of this data. And the unfortunate thing, or the thing to really remember, is that none of this slide makes sense. Okay, because one of the postulates of special, not even general, special relativity is that there is no canonical choice of time and space. So what on earth can I mean by an arrow that's supposed to represent time? Because maybe you do your evolution and you say, Zoe, this looks really bad, everything's blowing up. And I'm like, mate, you just chose the wrong coordinates. Yeah, choose better coordinates. Okay. So this is one of the subtleties with taking this evolutionary perspective is, you know, what, let's say, evolution in what time? What coordinates am I using? Okay, so this is a problem that was, you know, it's been solved by Choquet-Bruhat, Yvonne Choquet-Bruhat in the 50s, and then later also with Gerach. They studied the Einstein equation. So here I've just ignored the matter. And they used a very particular set of coordinates called harmonic coordinates. Okay, and they realized, or he found, I guess, in her thesis, is that if the data are constrained, okay, then the evolution under the Einstein equations 1, okay, is equivalent to solving this system of equations here, which I've put a star on. Okay, so instead of solving this system, reach E is equal to 0 here, if I use harmonic coordinates and I constrain my data, then the evolution equations are equivalent to this system star. Now, this system, I guess I should just do the next one here. So what is this system? Okay, with the star. Okay, so the box is what we call the reduced wave operator. Okay, it's some particular contraction involving your covariant derivatives and your metric G. Okay. Actually, I could even put partials here. Maybe I should put partials. Okay. And what are the coordinates here? Well, they are the harmonic coordinates. Okay. So this is a system. Okay, because remember, I have to solve for each mu and u, for each of them ranging over the different ranges, 0 to n. Okay, this is a system of nonlinear hyperbolic PDEs. And that's fantastic because we know lots of things about nonlinear hyperbolic PDEs. Okay, we know that we have local and time world oppositeness. We know that we have Cauchy stability. We know that we have finite speed of propagation. We know lots of things. Okay, and maybe if you don't, you know, if you're not in the world of hyperbolic PDEs, just the intuition to have is that solutions to this system of equations, okay, this star, radiate in time. Okay, and what is that time? It's this harmonic coordinate time y0. Okay, and very loosely speaking, this is kind of at the heart of the Einstein equations. We have either this or some equivalent hyperbolic PDE system. Okay, and this is why LIGO, the gravitational wave observatory, that's why they detect gravitational waves. Okay, they're not detecting dissipation or something. They're not detecting another kind of propagation. It's wave propagation that it's detecting. And it's kind of loosely speaking, this is where it's coming from. Okay, so these are the equations. So what could you ask? Okay, now that I've given you the initial value problem, I've given you the PDEs, what kind of dynamical questions could you study? And I definitely don't study all of these. I just wanted to give you an overview of what kind of people do in my field. Okay, so the first thing you can actually do is not even worry about the evolution, but just worry about the data. Okay, worry about this geometric data and ask, well, does there exist data that satisfies the appropriate constraints? Okay, and what can we say about this data? Can we make sense of it in some reasonable notion? Can we measure things from it? Okay. You could produce, and this is literally what lots of people do, produce numerical solutions, okay, to your system of PDEs and use that to match against observations. Okay, and this is what people do in gravitational wave astronomy. They have their equations. They probably don't use the same coordinates that I use. They wouldn't use harmonic coordinates, but they write their equations down in some particular coordinate system. They solve these PDEs numerically. They produce from that waveforms, and those waveforms are the things that they then match with what they test at LIGO. Okay. So then this is something I do, is I like to study special solutions. Okay, and one thing you can ask is what I guess I've already told you a bit about is, can I show stability? Can I take initial data, a small perturbation of initial data away from some special solution, and can I show that the PDEs exist globally in time, that I have decay, I have stability, let's say, global well presence. And let's say the motivation for this is that most of the Einstein equations, they're highly nonlinear. It's very hard to write down explicit solutions. So to do that, we've always put in symmetry, spherical symmetry, lots of different things, toroidal symmetry. And, you know, our world is not exactly symmetric. Okay, so you would hope that if I have an explicit space-time that I would like to use to describe the phenomena that I'm observing, you would hope that that space-time is also stable to some reasonable class of perturbations. Okay. And something else a lot of people do is study singular behavior. Okay, so general relativity, it admits these very weird solutions, very singular solutions called black holes. And I live my life avoiding black holes, and I'm happy with that choice. But yeah, you can do lots of things there also. And I guess, yeah, maybe I just mention it also. We use general relativity to build cosmological models. Okay, so not just isolated systems like black holes, but also cosmological models to describe our universe, to describe our Big Bang. Okay, and in particular there's lots of things that you can do to study the nature of a Big Bang. Okay, is the blow up that you get, is it generic or is it special? What kind of behavior do we have? Okay, so here are a few of the names of people that work in these kinds of problems. And I guess I just wanted to really highlight Robert Bartnick. Okay, so he very much worked on this top point, understanding the data. Okay, what we can say about the data. And there's also Todd Olenek, who's down in Monash, Volker Schluer, who's down in Melbourne, and lots of other people. Okay. So you've always got to be careful hearing a talk from someone that does general relativity, because there's no canonical choice of time, right? So I could just relabel it and just talk continuously. Okay, so now I want to tell you a bit about some of the stability questions, or the stability question in particular that I've been quite interested in recently. Okay, so we've met Minkowski, right? The simplest vacuum solution to the Einstein equations. And I guess here I've just put it dx with the bold face to represent dx dy z. Okay, so this is the most basic solution to the Einstein equations. Is it stable under them? Okay, you bloody well hope so, right? If it isn't, then we probably need a different theory. So the question to have, okay, so this is my kind of picture. My manifold is R3 when I take my time slice. So my initial data is posed on R3. I know I put a bump here that's a bit misrepresentative because for Minkowski it's just 0. Okay, it's just everything 0, but let's just imagine a bump just for visual purposes. And now I say, okay, I'm going to add a little bit of energy. Okay, I have a Riemannian metric on this R3 space, so I can write down nice Sobolev spaces with respect to that. Okay, and I say, okay, if this bump is small in HS, where I guess S needs to be big enough, 3/2, something like that, 5/2, I'm not so worried about that. What happens when I evolve it forward in this harmonic time Y0? Okay, do I get back to Minkowski, or do bad things happen? So the answer is yes, it is stable. Okay, and maybe in a couple of slides, I'll tell you a little bit about why it's difficult, a little bit of the maths behind it. It's asymptotically stable, so that means a small perturbation will kind of radiate away and I just get back Minkowski. And I guess I just want to convey a bit, like, it's a very hard problem. Okay, this first paper, it's a book, it's 500 pages long. Okay, I know it's a really simple solution, but the equations are just kind of, they're tensorial. There's a bunch of them. They're very complicated. Okay, it's nonlinear PDE theory. It's a mess. Okay, so this was one proof, the first proof by Christodoulou and Kleinemann. And it's interesting to note they use a different coordinate system. I've mentioned this harmonic coordinates, harmonic time Y0. They use a different time. Okay, they actually use different coordinates. And for a long time, it was believed that we could not prove stability in harmonic coordinates. Okay, because don't forget, once you choose your time and space coordinates, your PDEs, just the literal things they are, change quite a lot. Somehow it was thought for a long time that you couldn't show it was stable. And luckily, I mean, that's false. Okay, so Lindblad and Runyansky, they showed it in harmonic coordinates. They showed it is stable. Okay, and the paper came out a lot earlier. It came out in 2003. Okay, and then there's lots of other approaches. I guess I'll mention the micro-local approach of Hinz and Bashy, just to mention you can come at this problem in lots of different ways. often when I talk to physicists, they're like, well, of course it's stable. How could it not be stable? And I just like to remind you of the double pendulum. Okay, so, you know, this is a nonlinear system. It's got incredibly chaotic behavior. Okay, I have nonlinear PDEs. It's you know, it's very much unclear from the get-go that things are going to be okay. All right. So this is Minkowski. What am I interested in? I'm interested in Kaluza-Klein. Okay, so Kaluza-Klein is built out of Minkowski. So I take Minkowski, 1 + 3 dimensions, and I add to it an extra dimension, which is a compact circle S with a flat metric d theta squared. Okay, so this is my metric. And again, we can ask the same question. Is Kaluza-Klein a stable solution under the Einstein equations, under the vacuum Einstein equations? Now, lots of people, so I'll explain a little bit where this spacetime comes from next. Lots of people have thought about this. Witten said it should be stable. Okay. And for reasons which you could ask me about later, Penrose said it shouldn't be. He said it should be unstable. And so somehow the addition of this extra compact space was really thought that could change lots of the dynamics. Okay. And I guess the intuition to have in mind is that we have all the problems of Minkowski, which took 500 pages to prove, God forbid, and now I'm adding in an extra compact space. And this picture here is supposed to represent the idea that I have my initial data, I have my initial bump of energy, and then I kind of let it go. And I'd like it to radiate away. But if I have a compact space, K or circle, that little bump of energy could get trapped in that circle. And we could imagine that it gets trapped and it kind of focuses in on itself, maybe leading to some kind of regularity breakdown. Okay, so the intuition behind why people weren't sure if this space-time would be stable. Okay, so why do we're going to say a bit, why do we care about Kaluza-Klein? And it's a very classical model, goes back to work in the early 1900s. And at this point in time, we only knew about 2 fundamental forces, okay, gravity and electromagnetism. The strong and the weak force had not been discovered yet, not for decades. Okay, so Kaluza had this beautiful idea. He was like, well, why don't we unify these things? Okay, now one way to do it is to just put gravity on the left-hand side of the Einstein equations and electromagnetism on the right-hand side. Okay, that's nice. Is it pretty? It's not pretty. Yeah, maths is all about being pretty. Okay, so Kaluza, I guess Klein in different capacity, they realized the following. Okay, so if I go to 5 space-time dimensions, if I go to 5 space-time dimensions and I look at vacuum gravity, so no matter, okay, my metric tensor capital G has 15 unknown components. Okay, it's symmetric. 15 is conveniently the same as 10 + 4 + 1. And why is that important? Because if I go to 4 space-time dimensions, there are 10 components of the metric tensor, 10 components that degrees of freedom that encode gravity, 4 degrees of freedom from electromagnetism. Okay, this is in the Lorentz version, so that's why I have a vector potential, not E and B here, but A, the vector potential. And 10 + 4, I have 1 left over. And you work out that just on all the way things transform, it has to be a scalar field. Okay, so kind of Kaluza's idea was, well, could we somehow take this theory and encode it in this vacuum higher dimensional theory? Okay, which is great because vacuum is indeed prettier. Okay. And so Klein was the one who came along and said, well, this extra dimension needs to be small. Okay, it needs to be like a hosepipe view from very far away. You only see 1 dimension. Okay, it's only when you get really, really close, when you have enough energy that you can probe this small compact direction that you could actually see it. Okay, so the idea being that, you know, just like we needed lots and lots of energy to probe the Higgs field, right, we need even more energy to be able to probe a kind of compact space like this. Okay, so that's supergravity, kind of the baby version. And you actually can make this concrete. I realize I am actually running short on time, your time. So roughly speaking, if I suppose that because this compact space is so small everywhere, I could assume, okay, that actually all my tensors, they don't depend on this compact coordinate. Okay. Now, if you make that assumption, you can reparameterize your metric, okay, into 4-dimensional tensors 2 tensors, 1 tensor, and a scalar field. And your vacuum Einstein equations imply this following system here. Okay, and why this system is quite important, or why the whole reason why I put it on this board for you, is if I set phi to be 0, okay, then this vanishes. Ignore this bottom equation. If I set phi to be 0, that vanishes. I get exactly the Ricci tensor is equal to the correct electromagnetic tensor that I want. Okay, it's kind of miraculous, I guess, that works out. Okay, this will give me Maxwell's equations. That's good. The only problem with this is if I put phi to be 0 on the left-hand side, then dA must be 0 on the right. Not very exciting. Okay, so it's not, okay. It's not, it doesn't quite give us, let's say, the original goal that Kaluza and Klein had in mind, but it's still a theory that is, let's say it's the baby theory that's used in supergravity. Okay, it's the baby theory that's used. And when I say supergravity, I mean where we're trying to unify gravity here with non-abelian gauge theories on the right-hand side. Okay, so not just here, it's an abelian gauge theory, here it's U1, but also non-abelian, so SU2 times U1, things that we see in the standard model of particle physics. Okay, so this is just the baby version. Okay, so what did we show? So this is the theorem. Okay, so we showed that indeed Kaluza-Klein is asymptotically stable under the vacuum Einstein equations. And maybe in my last 5 minutes, if that's, oh yeah, okay, maybe in my last 5 minutes now, I'd just like to tell you a little bit about this. Okay, so there's, people did other things before. Okay, so there's definitely very important new insights from my paper by my collaborators, and Stingo. There's also somehow the PDEs that you end up studying involve wave and Klein-Gordon type PDEs. And one of the works relevant there is something I did with Shijie Dong, who's now in southern China. You always have to worry about whether or not you have initial data that satisfy your constraint equations. And this has been studied by Dai and Valku. Okay, so let me tell you about PDEs, right? The evolutionary perspective, which is what I'm particularly interested in. Okay, so remember we wanted to study that a system of equations that I denoted by star. Okay, so here I've written it out. And I guess I've really explicitly put out here the summation convention. Okay, so it's a second order PDE. Everything here is kind of perturbation. Okay. Now, since we suppose we have small initial data, it makes more sense to consider as our dynamical variable, as our fundamental variable, fundamental unknown, sorry, not G, but a perturbation of GH. Okay, so if I substitute this in to this equation here, I get the following system here. Okay, so where I'm thinking here, I want H to be order epsilon. I want it to be like the data. I want it to be small. Okay, so this is the system of PDEs that I want to study. Again, it's a system, mu and u range over all the different ones, possibilities. I've got the wave operator, box, the usual wave operator that you know, minus dt squared plus the Laplacian. I've also now got the Laplacian of the circle, d theta squared. I've got a quasi-linear part here, and I've got a semi-linear part here. So your hope is to get small data global well-posedness. And for these kinds of systems, quasi-linear problems, we typically use the vector field method, okay, which is developed a lot by Klein. Okay, kind of using, it's very hard to, almost impossible to say, to use the Fourier transform. Okay, so we use something called the vector field method, which is intimately tied to the symmetries of the ambient background geometry. Okay, so symmetries here coming from Minkowski and also the circle. I guess I'm not going to say too much about that. But let me tell you, so I guess, if you don't work on these PDEs, you might look at this and you'd be like, it's probably okay. So let me give you some examples to show you why it's not okay. So situations when it is okay is when the right-hand side is 0. Okay, so we know, for example, that linear waves with compact data disperse, okay, at a rate inversely proportional to time. Okay, very good. What happens if I just add a very simple nonlinearity to the right-hand side, dt squared psi? Okay, keeping in mind that in here, there are hundreds of terms like dth squared. Okay, maybe not hundreds, but a lot. There's hundreds of terms in there, and I'm sure lots of them are dth squared. Okay, so if I just have one of these, okay, box size equal to dt psi squared, Fritz John showed that we actually have finite time blow up. Okay, so your idea that these things disperse Maybe here I get a bit more smudgy and it disperses a bit slower, maybe. Your hope that actually I have global world closeness, that's out the window. But it turns out that, in fact, some nonlinearities can be good. If I just change this nonlinearity here and add a minus dx psi squared, okay, then Christodoodle and Klein-Gordon separately show that I have small data global existence. Okay, so just a very small structural change in the right-hand side, very different PDE dynamics. Okay, so let's say this is what happens in Minkowski stability. Okay, you've got critical decay. This T-1 decay is really critical for everything. And you need to understand lots of your nonlinear structure. Okay, so what happens in my Kaluza-Klein problem? We can actually go to the physics literature to get some heuristics. Okay, so these are my PD systems here. Got lots of things to worry about in this right-hand side. Just momentarily, let's do a Fourier expansion. And I said I wouldn't want to do that. Okay, let's do a Fourier expansion in this periodic direction. So I write my tensor H in terms of its Fourier modes, HL. When I substitute this in, okay, just into this principal part here, okay, I pick up, okay, my exponentials, they're still there. I pick up box minus L over R squared. Okay, so what do I observe? I observe that when L is 0, my 0 mode is like a wave equation. And my non-zero mode gives me a term here, which is a mass, which I can interpret as a mass, which is a Klein-Gordon-like equation. Okay, so what this tells me is that hidden within this system, I have wave-like behavior, and I have massless wave-like behavior, and I have massive Klein-Gordon-like behavior. Okay, so this is important. You need to distinguish these two pieces. Okay, I need to know if I have a wave-like interaction, which leads to blow up, because actually that changes. If I had a mass term, well, no, this nonlinearity doesn't lead to blow up. You need to be able to distinguish between those two cases. So this is what we do. Okay, so that, but instead of studying that infinite sequence of the Fourier modes, H0, H1, H2, we just divide them into two. Okay, we take the 0 mode, okay, which is just the average over the circle, which here I've called flat. Okay, that's the notation that we use. And then I have everything else. I have essentially the sum of all the non-zero modes. Okay. It is very important that we're on a flat torus to be able to do this. Okay. I would love to be able to do it on something else, but not yet. Okay. And so what we now do is we now study these two pieces. Okay, so you get PDEs like this. And I know they look quite scary, but I guess what I'm trying to say is I get now a wave equation for this massless term. Okay, and I get quasi-linear bits, all this other junk. Now I get a different kind of equation for the non-zero, for the Klein-Gordon term, and all this other junk. Okay, but now in the interest of time, I think maybe this is a good place to stop. But I guess I'll just say two things. Okay, so the first thing is we now have to really unpick this wave behavior when the wave interacts with a Klein-Gordon-like piece. When the Klein-Gordon-like piece interacts with a Klein-Gordon-like piece. So you have to kind of unpick these different propagation behavior. So this is what we do, and this is what we show. But for me, at least, this is not this is not the end point. Where I'd like to see it going is the following. So here I took Minkowski times a circle. But the main models that people use in supergravity is this circle is replaced with a Calabi-Yau manifold, okay, or a manifold with special holonomy that's not the torus, okay. And I have a work, I'll leave it here. You can read it, but I have some preliminary work, let's say, which starts to be able to treat these non-trivial compact spaces, but to be able to do this kind of refined projection and things like that on Calabi-Yau manifolds, that's, I guess, a long way off. So with that, let me thank you very much for your attention.
Wondering what you meant exactly by asymptotic stability. Is that stability in space or time or?
Yeah, both. And I guess it's showing that your perturbation, little h, decays to 0. Yeah, so it actually kind of, it really is, let's say, disappearing And what you're left with is something that is asymptotically Minkowski or Kaluza-Klein or whatever it might be.
The Klein-Gordon type scenario, there are special cases, as you know, the Klein-Gordon type equations, which admit Rieger solutions, which are sort of stable solutions.
No, yeah, I think that's it. I think the kinds of initial data that we consider rules out this kind of thing. Like it doesn't, let's say, it doesn't asymptote to something like that. Yeah, no, it's good. It's a good point. Sorry, you had a question?
So first you told us about this method, take a time slice and go from there. But it seems in your sketch of what you do, you didn't take a time slice. So did I see this?
No, sorry, no, I did.
Spacetime.
Right, okay. Okay, so I was studying hyperbolic PDEs, and if you just think, how would you normally study the wave equation? You would specify data at t equals 0, specify the function and its time derivative, and evolve that forward. That's kind of literally what I'm doing, but instead of my unknown being some scalar function phi, it's this metric tensor. Okay, so it's very much this initial value problem that you do for the wave equation here for the metric. Good point to be like, well, why do I need to specify anything? So this goes back, unfortunately, even though the theory is covariant, it doesn't depend on what coordinates you use. When you want to understand something like dynamics, you need to break that covariance. And again, it's this problem where you could be measuring, let's say, behavior, dynamical behavior that's really chaotic. But in fact, everything that you could be measuring could just be a coordinate redefinition. It could just be a gauge freedom. So you'd never quite know if, and this actually does happen even in the PDE. Sometimes you fix your coordinates, you solve your PDEs, and a term's not going to 0. So this happened for a black hole stability problem. They had to redefine their coordinates to essentially take out the term that wasn't going to 0. Like there was something that was obstructing decay. It was a unphysical degree of freedom. You kind of have to mod it out. Yeah, but there is, I mean, there's certainly an element. Okay, you could also say, what if I don't want to take t equals constant? You could take other hypersurfaces. You could take null hypersurfaces. In different scenarios, you even have a boundary. So there are different things also you could do there.
But maybe not. Sorry, I have the basic, but what are the heuristics?
This just means that if I mean, you could just think of this as a function. If I put a flat on the function, it means I integrate that function over d theta. That's all it means, yeah. And the hash means or natural, sorry. It means that I take my original function and I subtract off its 0. Yeah. Yeah, that's it. Yeah.
Yes, so there are no more questions. Let's thank the speaker again.